Hey everyone, this is Matt with Learn Everything About Design, and in today's video, I'm going to finally answer a question, or at least do a video talking about storing energy in 3D prints. Now, a while ago, we did a video where we talked about designing this, what I call the Q-tip blaster. And so that video, we focused on the different steps to storing energy. We did a couple of tests. So for example, we looked at doing a lot of these little strips, and we looked at doing just a couple of thicker ones with rounded corners. And ultimately, the design is this version. And this has a combination of those thicker spokes with the rounded corners or filleted corners. And the main key here through all the testing that I found was this little slot at the top, giving it the ability to flex. And what I found with trying to store energy in 3D prints, that flex is extremely important. Just using the properties of the plastic material, whether it's a PLA or an ABS or a PETG or something else, they're all going to have this point where the plastic deformation happens and the parts ultimately fail and don't return back to their original shape. So I've got a couple of examples here. In this video, I'm going to talk a little bit about essentially the way that the load goes through the part. So these are typically stress risers, and this applies to mechanical parts that are made out of metal, as well as these 3D printed parts that we are designing here in Fusion. And some of the key takeaways at least the one key takeaway that I hope we get from this video is the ability to think about storing energy by allowing for the global deformation of the bodies. And what I mean by that is the example that we're going to look at here is essentially using a slot and dividing up the 3D print, allowing it to flex so that we are reducing the point load or the stress in a single location. Whereas when we've got these stored energy tests, essentially what we're doing is we are fixing these upper corners and they're seeing a lot of stress. And we can only go so far as to let this inside piece deform before we ultimately have a problem. And so again, hopefully through this video, you'll be able to identify these types of changes and hopefully apply them to your own design. We are still focusing primarily on 2D problems. And what I mean by that is, in general, you can create these types of sort of stored energy designs or prints in 3D, which is a lot more complicated to understand the mechanics, so they can twist and compress in those directions. The problem is that on an FDM style printer, those are much more difficult to print and produce. You really need to have like a self-supporting process like an SLS, but those are going to be all nylon and glass filled and typically going to be a little bit more flexible initially, but they'll get more brittle close to those corners. And if we had a liquid process like an SLA, that might be more beneficial in these cases because then we can do some complex 3D shapes. Then we still have to deal with supports and post-processing and stuff like that. So for this video, we're going to focus on keeping it 2D. And so what I want to talk about first is stress risers. And typically a stress riser happens at a sharp corner in a design. Now we see this with 3D prints. When we try to create a 3D print, I don't really have a good example here on my desk, but if we try to create a 3D print with a sharp corner and we bend it, it is going to fracture at that corner. Now, another thing to keep in mind is the print orientation does matter. So printing something vertically, so in this case, if we look at it from the side, if we were to print it in this orientation, we would have a layer line right here. Now, there are some tricks that you can do inside 3D print slicers to sort of bury this down into the rest of the body to make it a bit stronger. But basically what we're going to end up having is a layer line or a shear point where it can just peel apart. Now, if we put a filleted or a rounded corner there, it does help, but we still have the same process and problem because of that layer line. Now, if we print it in a different orientation, let's say that it's printed in this direction. Now we've got a single layer line that's going throughout the entire design. And even though each layer is 0.2 millimeters thick, they stack up on each other and they are opposing, or they're in a different direction of load. And so as we load these designs, we need to think about the way we create the geometry, but also the orientation that we set them up to print. And so what I really want to focus on with this design, and this is just, again, a very simple example. basic simulation that was run in Fusion. If you do a static stress simulation, it's free to solve. So if you're on a commercial or an EDU license, you can do that. I think the hobby license might not have access to simulation because it's cloud solve. But the main takeaway here that I want to point out is that with the sharp corner, and this is exactly the same load, the only difference between the two is the actual rounded corner. But when we look at this, we have got the stress that's sort of concentrated in relatively the same area from left to right. But what you'll notice is this green section is actually down here in that corner. And then this darker blue section, which is essentially where there is little to no load, is going all the way down into the root of that area. And so what this means is that all of this deformation, all the load that's happening in this corner is going to cause this thing to fracture right there at that corner. Now, if we go to the version with the rounded corners, what you'll see is that darker blue section is actually pushed up quite a far way away from those corners. Now, these are obviously they're rounded and they do look tessellated, and that's because you actually have a mesh. When you're creating a simulation, it uses a mesh. So depending on the resolution of the mesh, the results will change. If I turn the mesh on, you can kind of see what we're dealing with here. I'll do the same thing for this one. So if we created a finer resolution mesh, I would expect those to come down a bit more. And I can edit that while we're doing this video, and we'll let it solve and come back to it. But the thing that we want to look at is going to be the fact that, one, the max stress value, so that red area, is a smaller number. So 3.2, where this one is 4.2. And if we isolate those red areas, and we'll do that over here as well, you can see that it appears that it is across a little bit of a larger area, and it transitions gradually back into that corner. On this one over here, if we zoom in, you can see that this one is narrow at the top. It gets thicker close to the corner down here, and there's a sharp transition that's happening here. And so the difference between these is going to be, again, one higher load in the version with the sharp corner, and the concentration of the load is in a different area. And so this is why with most mechanical designs, especially in the direction of load, you will actually see there is a rounded corner, even if it's very small, because that'll help spread the load out over a different area. So what I'm going to do is I'm going to finish compare. I am going to modify the mesh. So I'm going to just edit this. Currently, it's based on the part size, and what I'm going to do is I'm actually going to go into advanced settings, and we'll set this a bit smaller. Let's see, we want to do minimum element size. Now let's go ahead and let's go ahead and just bring that down. We'll say okay. Higher memory consumption, but we'll resolve it. So that's simulation model 1. I will do the exact same thing here. Just bring that down. Generally, it doesn't like it to be this low, but these are small parts. It's not gonna be too much. All right, and so what we're gonna have to do is we're gonna have to resolve these. So I'm gonna go ahead and solve this one. We'll solve both of them, and then we'll check back in on them. And so if we go back to, again, the stored energy test, close. The main thing here is that in this design, what we have is, instead of, this is a nice rounded corner, so the load itself would be able to transfer around without creating any of these spikes. So that's the first step in this process. But the second step is that we need to have that deformation of the plastic. And if we have a thick section like this, even if it's got infill and we're not trying to deform the inside too much, but if we have a thick section like this, what's going to end up happening is it's going to not be able to stretch out on the outside edge or compress on the inside edge, which is typically what happens. And so what we end up doing is we make these thinner sections, and when we print them, they will not have infill. They'll be sort of homogeneous, so we'll have trace lines in through all those sections, and I'll go ahead and I'll slice this and show you. But basically what we're doing is we're allowing these smaller sections, this inside to sort of compress the plastic and the outside to stretch, and the same thing to happen on the outside. And what we end up finding out, and it's probably not going to show on this camera, but what we end up seeing is that they get closer together. So when we squeeze this, they actually will get closer together because the inside one is a little bit more rigid, and it's allowing the outside one to flex, and then they kind of compress together. And so a use case for this is a carabiner. So I was sort of sitting in on a CAD training class that I was supposed to kind of review, and they made a carabiner in that. I'm not going to name any names. I don't want to call anybody out, but they made a carabiner in that class, and it failed. It basically deformed, and it wouldn't spring back. And so I was looking at this and thinking, well, how can we turn this into something that does actually spring back without going into plastic deformation and make it actually work like a true carabiner? Now, I wouldn't put any load on this, by any stretch of the imagination, but the little hook, it actually will hold, will hold some weight. But there is a limit to this, but essentially we've got a section that allows for the inside to flex and the outside to deform and compress together, creating that spring. And so this can be used to do all kinds of cool things, like make latches to latch multiple pieces together, make little catapults, use them as springs inside mechanisms. The key takeaway here is really that we are focusing our attention on allowing for the deformation and rounding all the corners so we don't have any stress risers. So I'm going to go ahead and slice this, but let's go back to the simulation and we'll take a look. And so what I want to do is, once again, I'm going to compare. So this one here is going to be, let's study 1, study 2, that's fine. So you can see we now have smaller mesh elements. With the refined mesh elements, you can see now that load is going further down into that corner. And you'll also see, let's go ahead and pull this back, the stress number for the maximum stress here has actually gone up. So the smaller element size gave us better resolution to identify where that stress was going and also to really identify the maximum amount. And so what we're going to see here is in the sharp corner example, we've got it really concentrated around that edge. And again, this is where it's going to deform and where it's going to break. And in the rounded version, you can see where it's concentrated is the transition between the fillet and that flat section. And so even though this is curvature continuous, what this is going to do is this is going to end up causing the deformation to happen in that area, assuming you get to the point where you get into plastic deformation. So this one will likely fail and break pretty early. This one will go a bit longer, but the failure point will be right there where that fillet ends. And so as we're looking at these designs, if we were going to try to figure out how to make this design work and flex and move around, and full disclosure, I haven't done this before, so we're actually going to go ahead and make it, and then we'll print it and test it out. But if we were going to try to make this a design that allowed for that flex without having it cause that deformation, what I would do is I would create a sketch. I always do that. I create a selection set more times than I like to admit. But what I'm going to do is I'm going to create essentially a slot inside, which will allow these upper faces to pull away. So this one on the left side will actually push down, and this one on the right side will push up. And I want to carry that up into the center here. And I'm not using any dimensions here, so I could be more precise and use some actual dimensions. For this example, I don't really care. I'm going to go ahead and just make it look okay. And we'll go ahead and just pull it all the way through. And then again, because of stress risers, we want to round these corners off. Now, in an ideal world, we would want these to be a consistent thickness. And so to get a consistent thickness, what we would do is just use an offset. Again, for the purpose of this video, I'm not going to stress over it. But what I want to do is, again, I want to keep them relatively the same. And then I'm going to add a small fillet here. These ones over here aren't going to see enough load to cause a failure at those points because the load is going to be going in the negative x direction, or in this case, the positive as we're looking at it, or to our left, to my left. And so what's going to happen is this piece will come down, this piece will come up, and it will allow for enough deformation in the system that we won't get into that permanent plastic deformation. And so let's go ahead and I'm going to slice this. So I'm going to save this as a mesh. Send it to Bamboo Studio. Do a little elevator music. It's a good time for me to get a sip of tea. All right. I don't know why it's taken so long to load. Oh, I have an instance of it open already. That would be why. All right, so let me slap this thing down on the bed. We'll slice it. And so as we slice it, what I want to look for, this might be hard to see, is you can see what it's starting to do is put some infill on the inside because it's consistent thickness here and it's not consistent here. So this to me is a problem, and I really want this to be a consistent thickness that will allow me to better understand how it's going to deform. So in my strength section, I'm going to increase the wall loops and I'm going to reslice it. And you can see now there's a little bit of a break there, a start-stop point, but now it's consistent all the way out to here. And we've got at least 3 traces or 3 walls that go all the way around that geometry. Same thing up here. We could add 4 if we want. It would just push it further up here. But that gives me a pretty good indication. I need to connect my LMS. I need to connect the AMS. And I'm going to go ahead and print that just in blue. It shouldn't take that long. I'm going to go ahead and allow that to go. And so while that's printing, let's go ahead and hop back into Fusion and talk about the carabiner as well. And so the carabiner is the same thing. So what I'm going to do is I'll save this as a mesh, and we'll slice this so that way we could see, and then we'll come back when the printer's done. All right. So once again, I'm going to slice it. I'm not going to print this one again, but I do want to highlight this. It would be easier if it was a different color. I got to do it over here and prepare, just so we can see it a bit better. All right, and so here's the thing that we want to watch out for. Again, you can see, maybe you can. You can see that the walls end up before this sort of section here where we transition from an arc to a flat. And so what I would want to do is go back and increase the number of wall loops and reslice it. And what I really want to see is those wall loops to go out and around the part. And if they're still not there, I would maybe add another one and reslice it. And we really want to make sure that we focus the focal point of the stress away from any of these corners. And so having these be continuous wall traces and not infill, for example, will allow me to ensure that any deformation happens away from the transition from that arc to that straight section. And so again, this is not just a case of the design itself, it's also a case of the orientation that you print it and the slicer settings, and all those things are going to come into play. So I'm going to go ahead and pause and let this piece print. We're going to test it out, and hopefully I don't have to redo this video because I made a mistake. But we'll check it out. We'll see if it deforms how I anticipated and whether or not it has that springing action that we want. All right, so it printed. I will put a little video on the screen because the webcam's probably not going to work very well, but it behaved as expected. And so as you push or pull it, the side that is opposing the force, so in the screen, if we push it to the left, this side over here is going to compress down, and the other side will be able to extend or kind of raise up. So anytime we're trying to store energy in a 3D print like this, we have to remember that we are going to be limited to what the material can withstand. A material can only withstand so much deformation. So the main goal is for us to spread out the deformation as efficiently as possible. We do this by using large fillets. So in the case of the carabiner, you can see that we've got basically the ends are very large arcs, large fillets. I did put some fillets and chamfers on the corner. Those do tend to help in some cases because, again, we're getting rid of those sharp corners. In our case, probably not as big of a deal. But again, they do add a little bit of structure to it and help get rid of those stress risers. And when we talk about like the Q-tip blaster, again, the key to making this thing work was allowing for this upper section to deform and squish down. And so that's the big takeaway that I want you to have with this type of thing. There are going to be many different use cases or places where you try to create a spring or allow the plastic to deform. And keeping in mind that you can't just flex it and expect it to go back, that you really need to allow it to separate into thinner sections, allow it to deform in the direction that it wants to. And that will give you the ability to hopefully store enough energy in these that it will work. I do also, while I was waiting for this to print, I did create sort of a 3D spring. It kind of looks like a barrel. This kind of thing, again, it doesn't work real well because we're printing vertically with the layer lines. And really what we're trying to do in a case like this is as we compress it, we're trying to get it to spin because we want the deformation to happen gradually over longer distances rather than just at the corner, so for example, just at the fillet. So the intent with something like this is to change the shape in 3D. So it's not just vertical columns we're trying to compress. You can do zigzag shapes or large arcs or curves like this. But what we're trying to do is we're trying to get it to deform in that direction. I will go ahead and I'll put a couple files in the description of the video. I'll put the carabiner file. It can use some more work, but you can play around with it and see if you like. I'll also put just a couple of other things in there. And I don't do much on the Patreon account, but if you are looking for ways to support the channel, I'll also toss up the data sets on the Patreon page. And if you want to just buy them for $1 or $2 or whatever it is there just to support the channel, feel free to do that. They will, in this case, they'll be the same data set that you can download for free from the description of the video. So totally up to you. But if you have any questions on this, let me know. As always, thanks for watching, and we'll see you in the next one.